Okay. Hi, everybody from Grace Hopper. I have no idea when I'm in the screen or not. Okay, so this is actually a super important lecture, so I'm very glad that we are filming. Ta-da, the stack. um, this is a really important concept in computer science. When I introduce the data structure itself to you, you're going to say, great, but honestly, you're going to use it your entire career here and hopefully onward. Um, this material will not be on the midterm. It's just that I need to introduce it to you at some point, and the midterm is going to be next week, Wednesday? Yep. Okay. So I didn't want to skip a bunch of days. Okay, so first of all, the stack itself is just a data type. Hopefully you guys, have you learned about it yet in 103? Yeah. Okay, excellent. For those of you that haven't, just really quickly, we'll go over the idea, the difference between a stack and a queue. So a queue is what you are familiar with at the grocery store. If I am, we got shoppers A, B, and C here. If shopper A gets in line to check out first, and then shopper B gets in line, and then shopper C gets in line, shopper A is going to be done first. Get out of the line. That's a queue. Can anybody spell queue for me? Q. Excellent. I think it's tricky. I was all proud of myself when I first learned how to spell Q.
I pronounced it quay.
It's not quay. Unless maybe in French. I don't speak French. It's not quay. Okay. So, it could be a British thing. I have a really, really good friend that's British. He brought coffee to my morning class once. I'll have him bring stuff in here to you guys because he's very entertaining. Okay. So the stack data type, first of all, I mentioned it's going to be super important. We're going to use the idea of a stack with interrupt-driven I/O. So instead of when we want to pull those device registers to see if like a character's been typed, we're not going to say, hey, are you ready yet? Are you ready yet? Are you ready yet? Are you ready yet? We're going to do something useful and then let it come in and tell us when it's ready. So we'll be interrupted by that device. And then also for evaluating arithmetic expressions, old calculators used to work this way. We'll go back to after the second part of this lecture will be on that. Okay, so a stack itself, whereas the queue was a FIFO data structure, first in, first out, stack is a LIFO, last in, first out. And the nice thing about a stack is there's really only two operations. You can push something onto it, and you can pop something off. That's it. It's really simple. It's not like when you're going into memory and you have to say, I want to, let's say you have a register. I want to store this register and I want to put it here in memory. You just say, hey, I want to push this register onto the stack. Or I want to pop off the stack and put it somewhere. You cannot put it in a certain spot in the stack. You're always dealing with the top. Okay, so here is an example of a physical stack. I don't know, the older I get and the younger you guys get, the less this slide makes sense. But back in the day, maybe they still have cars where you push coins into a coin rest. And if I push that 95 quarter on first, then I push an 82 and a 98 and 96 quarter on top of that, the first thing that I'm going to take off is that 96 one. It's the last one I put in, is the first one that comes off. So I pushed 4 things on, and I popped 1 off. And that's all you can do to a stack. Push things onto it, pop things on. Always working with the top. Questions on that? I know you did it in 103, so I'm moving a little bit quickly. Okay, so that's a physical stack. Here's a hardware implementation of a stack. So imagine these are registers. We got 5 different registers here. And we're saying, okay, we're going to call that first one the top. If the stack is empty, that first one is the top. And I'll push the number 18 into the first register. And then if I want to push in 31, I have to move 18 down and then push 31 on. Then if I want to push on a 5, I move both of those down and push the 5 on. And then if I want to push on the number 12, I move all 3 of those down and push the 12 on. And then if I pop the 12 off, I have to move the other 3 up. And then I pop the 5 off, and I move the other 2 up. Okay. So even explaining it to you guys in English words, it was annoying. What was wrong with this kind of organization or this kind of design? moving everything. So if this stack was really big, if I had 1,000 things on the stack and I pushed something onto it, I'm gonna have to move 1,000 things down to make room for it. So this is a hardware stack. A better solution is to do it in software and just change our idea of where the top is. Put something into memory and say, okay, that's the top now. If I push something else on, push it in a different memory location and change where, and say, okay, now this thing is the top. So that's what this slide shows. This is a software stack. So instead of thinking of those as registers now, think of them as memory locations. And in a register, in this case I'm using R6, I'm going to keep what my idea is of the top of the stack. So right now I'm saying the top is memory location 3000. And I'm going to kind of draw this on the board to go along, just for fun. Okay, so right now R6 has 3000 in it. So we call R6 a pointer, the top of the stack pointer. Why would I call it a pointer? What does that mean?
Refers to location, right?
Excellent. So Kobe says it refers to the location of something. Its sole purpose is to hold the address of something. It is pointing at this memory location. So if this memory location is 3000, R6 is pointing at it. And I'm going to use this notation from now until the end of the quarter. Pointers are going to be huge. It's actually nice that I introduced pointers to you when we're talking about the LC3. And you can see it holds an address, and this is an address, and R6 is then pointing here. So when we get to C, traditionally pointers are the thing that freak everyone out when you learn the C programming language. And you guys will be good at it by the time you get there, because you'll be used to using data as an address as a pointer to something. So R6 is referring to this memory location. That is our top of the stack. What's the next memory location up from there?
2FF.
2FF, perfect. I think it's probably on there. No, it's not. Oh, not really. Okay. Good job for those of you that figured that out. Okay, so when we push something on in a software stack, the first thing we do is decrement the stack pointer before we actually push the data on. So I change my stack pointer to FFF, not P. There's no P in hex. I'm not inventing numbers. And so now R6 is pointing here. Then I store the data to where R6 is pointing. What LC3 command is that to store something to where the address is in a register? I kind of said it right there in my question. I'm storing something where the address is in a register. Store register. Okay. So store register, the address you want to store to is in the register. So that's what we're going to use for this. So I decrement the stack pointer and then I store the data. And so the way R6 is kept, our stack pointer, it's always pointing at our current top of the stack. So right now, so before it was pointing here and our stack was empty. And then as soon as we pushed that on, we decremented it and put the data on. So R6 is left resting, pointing at the top. Then, if I heard that, so we should have cookies at some point, unless that was my phone. Damn it. Now you guys got me swearing on video. Oh, that's not even my phone. Your phone.
No, my phone.
I don't know.
You can still get us cookies.
Cookies were promised, that's what matters.
Dang it. Alright. Since I then interrupted the lecture for the last 15 seconds, I should probably get cookies. Okay. Then we pushed the 31 on. That got pushed on next. So instead of just jumping from here to here, let's watch that happen. When I push the 31 on, I go ahead and decrement this stack pointer again to have it point here. And then store the data there. And so after that second push, this is what memory looks like. And this is now the top of my stack. And then you can see after 2 more pushes, that's what everything looks like, and R6 has this in it. Then, let me get up to that point. Alright, so we're here. R6 is pointing here, that's our top of the stack. So then when we want to pop something off, first you go ahead and you load the data from memory. So remember, these are memory locations. From the address pointed to by this register. So that's a load register. I'm going to load the, so with a push, we decremented the pointer first and then stored. With a pop, we're going to load first and then increment it. So I load the data out of here first because R6 is already pointing right at the top. So I load that data, put it in a register somewhere. And then I increment the stack pointer. So that thing's popped off. And now that's my top of the stack. I do that again, put this data somewhere else. Now that's my top. But all I did when I did a pop was load the data out of memory and increment the pointer. So is this data still here? Yeah, I didn't erase those memory locations. That data is still there in memory. I just can't get it with a stack operation because there's no stack operation that says, oh, add 1 to the top. There's no moving the top. All you do is push or pop, and the top gets moved when you do that. But there's no changing around the top just for funsies. You have to use a push or a pop. So the only way to access this memory is to push something else on. So I would decrement the stack pointer and push a different value in there. So even though it's still there in memory, it's not accessible with stack operations. Questions so far on the idea? Yeah.
So I know we use something like a queue
Uh-huh.
or something like a music playlist.
Okay.
So what would be like a practical application for this stack? Or for a stack?
Interrupt-driven I/O, which I'm about to get to. We're also going to use it for function calls. When we start learning about C, we're going to see how functions are actually translated. So part of what we're going to do when we learn C programming is have a section, a piece of high-level language like C, and we're going to translate it to assembly, to actual machine instructions. And when a function gets called, we need a stack for that. So you're going to see a couple of good examples, one of them right now, for what we use a stack for. Good question? All right. So here's just our, notice I'm using register 6 as my register to keep track of the top of the stack. Most normal processors would have a special register to do that. It wouldn't be one of your general purpose registers. There would be a register that was set aside just to keep track of where the stack is. In LC3, we're just going to use R6. So kind of from now on, you're not really going to use R6 for anything else. So I already took R7 away from you for return addresses, and now I'm taking R6 away from you. I'll eventually take R5, but I will leave you with R0 through R4. Okay, so R6 is what we're going to use as our stack pointer. So here is basic code to push and pop. So when I want to push something onto the stack, I subtract 1 from R6 and do a store register from whatever register I want, in this case R0, on to where R6 is pointing with no offset. Do a pop, I do the load register first and then add 1 to the stack pointer. Question? So what those last 2 pieces of code didn't take into consideration is we can have some errors with the stack. With pop, we can have an error when our stack looks like this, or actually I didn't need to erase these. When our stack looks like this, that means we've already popped everything off. When the top of our stack is pointing back here, our stack is empty. There's nothing left to pop. So this is a routine that does a pop that will not, that will give us an error. It'll let us know we failed if we pop an empty stack. So how the code works, I load into R1 the negative of where our stack pointer would be pointing if the stack was empty. So R1 gets minus hex 3000. Oops, I did that backwards. I compare that to the stack pointer and put my result in R2. So right now, if I add up these two, I would get 0, which means the stack is currently empty. So I'll branch on 0 down here to fail, and I'm going to put in R5 a kind of a return value, an error code. And in this case, I'm going to put 1 for failure. You'll get used to that when we get to C. I know that in some programming languages, you'll know that 0 means false and 1 means true. So it's kind of counterintuitive that you use 0 for success and 1 for failure. But the reason we do that is when a program succeeds, great, it succeeds. You only need 1 value for that. But if a program fails, there might be 6 different reasons a program fails. Or there might be 100 different reasons a program fails. So when you return some sort of error code saying we didn't succeed, you in general want to give some information as to why. So 0 means success, and anything else is some code saying why you failed. Maybe I couldn't open a file, I failed for that reason. I couldn't access the network, I failed for that reason. So we want to have a lot of values to indicate failure, but just we need 1 for success. So get used to 0 meaning success and anything else meaning failure when you're returning an error code. So we clear out R5 and put a 1 in it and we return. Nothing got popped from memory. We didn't load anything. We never did a pop because we're already empty. There's no popping that's going to happen. So R5 got a 1 put in it, we failed. But if we're in this situation, the stack isn't empty. Okay. So when I do that add, when I add R1 to R6 in this case, I'm going to get -1, which is not 0, so my stack isn't empty. And I go ahead and I continue. I load from where R6 is pointing into R0. So R6 is pointing right here, get that data. And then add 1 to R6, so increment our stack pointer. And then we need to indicate success, so just clear R5 to 0. And then return. So that was a successful pop. Questions? Yeah.
So is R5 going to be reserved for status codes?
It isn't. I'm actually gonna steal R5 from you for some other reason, but it's gonna be like 3 weeks from now. You use all R5 all you want before then. Yep.
Sorry, but can you quickly go over the x minus 3000 again?
Sure. So in assembly, if I want to fill with a negative something, I can do this. But really, what's in there is so this is positive 3000. So that's positive 3000. If I want to know what negative 3000 is, I would flip these bits. And then I'm going to add 1 to that. 1 and a 1 is a 0. Carry the 1. I'm going to get zeros all the way across here. Oops, left it there. Okay, so here we carried this, we got a 0, carry the 1, 1, 0, 1. So that is negative 3,000. I didn't want to have to figure that out in my head, so I just put that, this. But now, when I add this number, this negative 3,000 to this one, I would get a 0. Basically, wherever my stack pointer would be pointing, if the stack was empty, I put the negative of that somewhere so I can test to see if that's what the value of this is. There's no other way for me to know if this is at 3,000 except for subtracting negative of that and then checking to see if it's 0. That's why I put that there. If my stack started at 4,000, I would put negative 4,000 there. I want to know if my stack is at the empty spot.
So we just do that to know if we're at the end of the
If we're
stack.
at the end of the stack. That's why we're doing that. If there's nothing left. Because I know, I can ask you guys, hey, if you know that this is what my stack looks like, if I tell you guys R6 has 3,000 in it, you should just know stack's empty. That's the top. If the stack pointer has something, 2,000 something in it, you know, okay, there's something on the stack.
Is that why you have that gap at the bottom?
Yeah, so this memory location actually never gets filled with anything because in our push routine, we decrement the stack pointer first and then put the data on. And in the pop, we load the data off and then increment the stack pointer. So wherever our idea of the top is never going to actually get any data in it because the push decrements this first and then puts the data in. So at some point on a midterm or a final, I will probably ask you to draw what the stack looks like after some pushes, and the initial spot should always be empty because the decrement happens first, and then the data gets stored. Yep.
Is there any particular reason with Dawood moved the other way, where we push and then decrement?
No, I think it just looks nicer that R6 stays pointing at the top instead of having R6 be 1 up, and then when you pop, you have to decrement it. It could have gone either way as long as you were consistent with push and pop. Here is push with overflow detection, so kind of the opposite problem from trying to pop from an empty stack is pushing when it's full. So let's say your little coin rest in your car is completely full of quarters, you cannot push another one on. Same thing here, we don't want to go just pushing so much stuff onto our stack that we run into operating system code. Think of the LC3, everything below memory location 3000 is reserved for the operating system. If you've actually looked at that memory in the simulator, there's not a whole lot there until you get to below like 1500. So there's nothing literally between 3000 and 2000. So I'm saying, okay, we can have all that space for our stack, but we don't want to go writing above memory location 2000. So we'll say that means our stack is full. We have to protect our operating system memory area. So I'm saying if our stack pointer ever gets to 2000, no more writing to the stack, no more pushing. So this one does kind of the same thing as the other one, except when you go to add something, when you go to push, it checks to see if the stack is full, and if it is, it doesn't put anything on the stack, and it branches down here to put a 1 in R5. Otherwise, it goes ahead and decrements the stack pointer, pushes the info on the stack, and sends R5 to success. So that's overflow detection. We don't want to overflow the size of our stack. Questions? All right, finally back to what we're going to use this for. We're going to use it for interrupts. I briefly introduced it in chapter 8. We're going to go back to those slides. I apologize, I didn't bring new chapter 8 slides, so if you have them, you might want to get them out right now. And I'm going to go over that section again. Back to those. Okay, interrupt driven IO. This is where we are going to stop the ridiculous, if we want a key pressed, we are going to endlessly hold the status register until someone presses. We'll go ahead and we'll do some useful something while we're waiting for the key to be pressed, and then be notified when the key press happens. So we'll let some useful code run, and while that code's running, as soon as the key is pressed, we're actually going to force that code to stop. We're going to go run some service routine to go ahead and take care of that key that got pressed. And then we'll come back to the thing that was running like it never stopped. The problem being is that code that gets interrupted has no idea the interrupt's coming. It's just, it could be the Pig program that you wrote. It has, that one uses polling to get its keys pressed. It could be you're going to go ahead and print something to the screen, and all of a sudden you get interrupted. You have no idea that it's going to happen, and we need to be able to get back to that program when we're done servicing the keyboard, and have your program just work like nothing went wrong. So that's what we're going to learn how it happens today. One of the things we need to do, and you actually need this for your lab that you're working on, is going to answer question 1. One of the things we need to do is know when that key is pressed. So in hardware, we need to generate a signal when the key is pressed, so we can then know that it happened. So here's our keyboard status register, and bit 15, you guys have already seen is the ready bit. Here, I don't need to draw it. So when someone presses a key, that gets changed to 1. And then the next bit over, bit 14, that's the interrupt enable bit. If that's a 1, it means you want interrupts on. And that's something you set. You set it to 1 if you want it on. You set it to 0 if you want them off. This thing right here, does anyone know what this is called? This is an AND gate. Okay, so I got some CPEs in here maybe. This is a piece of hardware that has 2 lines coming in and 1 going out. And this thing is only on if both of these lines are also on. So if I have a 1 and a 1 coming into here, the signal gets sent. Kind of like a logical AND. Both sides of it need to be true for the whole thing to be true. Same thing here. Both sides of this need to be a 1 for this 1 to get sent. So if this bit is a 0, bit 14, that means interrupts are off. Because no signal is going to get sent if bit 14 is a 0, regardless of whether a key has been pressed or not. If there's a 1 in 15 and a 0 in 14, that signal does not get sent. But if there's a 1 in 14, and there's a 0 in 15, still no signal. But as soon as someone presses a character or a key, this gets changed to a 1, and all of a sudden they're both 1s, and we send the interrupt signal. So that's how the signal itself gets generated. And it's in the keyboard status register, that device on the keyboard. Questions? Okay. Alright, so not just anybody can interrupt anybody. Let's say the other running device that's super important at that time, the program that's running, is some temperature control program at the Diablo power plant. We don't want to interrupt it because someone pressed a key that needs to be for your Pig Latin program. So running programs have priority, and they have priority levels 0 through 7, so there's 8 of them. So our payroll program would run at level 0, that's our lowest priority, whereas some nuclear power program would run level 6. I would think level 7. Interesting, I don't know what level 7 is safe for, maybe it ran out of whiskey or something. That would be a big problem. Okay, so what happens is after that signal gets sent, the interrupt doesn't automatically happen. There's this priority encoder that then checks, is the priority of the device that is sending the signal higher than the priority of the program that's currently running? And if it is, then the signal gets generated. If not, it waits until some other thing is running that has a lower priority level. And that's what that's all about. Okay, so when do we test to see if the interrupt signal has been sent? Never in the middle of processing a single instruction. So let's say we're doing an add instruction. We've fetched it, we've decoded it, we know it's an add, we're right there in the middle of getting the operands from the registers, sending them down to the ALU. We don't stop it right there. We wait until that add command completely finishes. We store our result, and then before we go back and fetch the next instruction, we test for an interrupt signal. So we test for interrupt in between each instruction in a program. So if the interrupt signal's been sent, then we're gonna not go back and fetch the next thing in our program. We're gonna transfer control to an interrupt service routine. Kind of like if we do a JSR in our code, we transfer control somewhere else, and then we save our stuff to get back, our program counter. Here, we don't know that we're being interrupted, but in between two machine instructions for our program, we see that an interrupt's been sent and we transfer control to some other program. At some point, we're gonna have a way back, but we haven't seen how yet. So that's when you test. What I want you to get out of the slide is we're never interrupting in the middle of an instruction. We test in between the store and the next fetch. Yeah.
Does the keyboard status register bit flip in the middle of instructions?
Flip.
Like so, meaning that there's a key press.
Yeah, so the key would be pressed. As soon as that key's pressed, that bit comes on, regardless of whatever else is happening. And the interrupt gets sent, and then we go after the instruction and we see if the signal was sent. They're happening at the same time. Yeah.
So this whole element of pulling, even after an IO for the LCD.
This is instead of polling. Yes.
Like, I was
So we can have something else happening instead of asking over and over again, are you ready? Has something been pressed? Okay, so, oh, we did this already. That was back when we were first learning about I/O. So let's go back to our slides from chapter 10. All right. So we have this interrupt triggered, okay? And we have some program that's already running that's going to get interrupted, and we're going to go somewhere else and run some routine, some subroutine that's going to do something to the keyboard, and then we need to come back. Problem being is that the thing that's running doesn't know it's being interrupted. So let's look at the things that we need to save to make sure we can get back to a program and have nothing messed up. Okay, so let's say we have some program that has a loop in it. And as the last thing in our loop, we are decrementing some register that's storing a loop counter. Like maybe R4 has 10 in it because we want to run this loop 10 times. So, oops, -1. And then we will branch on positive back up the loop. So we are running this add. We're processing this add instruction. Right in the middle of the add, someone presses a key. So the add finishes, and we go ahead and we store our result in R4. Let's say it was a 0. Because a 0 was stored in R4, what gets set?
Z.
The condition codes get set. It doesn't matter what I put in R4, the condition codes are getting set. So there's also this condition codes register that has a Z in it. And then right here, we've stored our result in R4, but before we fetch this command, we realize the interrupt has happened, and we go somewhere else. We stop this code. We go to run code somewhere else. So what we need to save to get back, kind of most obviously to me, is the program counter. We need to know where to go back to. What else do we need to save?
Registers.
All of the registers. So all of the registers, including R7, because maybe this is a subroutine too. We need to know where this thing needs to go back to. So, the program counter, all of the registers and the condition codes. Because just restoring these registers isn't gonna do us any good when we go to run this instruction, because the condition code register has been mangled at that point. We need the condition codes returned as well. So when we go to run this thing, whatever they were set to, is what it was. Otherwise, we might miss the fact that that thing went 0 and then start going negative, and we'll miss the chance to break out of this loop. Okay, so registers, condition codes, and program counters. Those are the 3 things we need to save. How do we save those? The interrupt service routine that we're running, that's software. So we have some code over here. We could go ahead and say, okay, store the program counter. We actually can access the program counter using LC3 commands, which is tricky. I probably shouldn't write over here because that's off the screen. Huh? So we're pretending we have some code that's running somewhere else. So now we're in the interrupt service routine. So does anybody know how to access what the value that's in the program counter with the instructions that we currently have? Sam?
The other -1 offset.
Yeah, if you do an LEA, load effective address, basically that forms an address based on the program counter and an offset. And if you give a -1 offset, that gives you the program counter or the address of the instruction that's running right now. So you can get what's in the program counter. So the problem is, by the time I come to this other service routine, I'm already running. Let's say the service routine for the keyboard is at memory location 1F25 for no good reason, and I'm running the code there. By the time I get there, the program counter has already been changed, so I can't save it in software. This thing doesn't know it's being interrupted, so you can't save it here because it's just running along, and all of a sudden we start running code somewhere else. So even though we could access the program counter using LC3 machine instructions, by the time we get to the code that knows the interrupt has happened, our program counter has been messed up. Another problem is we also need to save these condition codes. And this register where they're at isn't accessible by any of the machine instructions in the LC3. We do know that this thing can go ahead and store the registers that it's going to mangle. So we don't have to really worry about the registers. This routine over here, any registers it's going to change, it can go ahead and save because it knows that it's changing them. But before we get there, we somehow need to save the program counter and these condition codes so when we go back they can be restored. So now that we know what a stack is, we can actually explain how that happens. First of all, these are all the things that we need to save, which we kind of just came up with together. One piece that I haven't shown you yet is that the condition code register I've been talking about doesn't just have the condition codes in it. It's actually part of a 16-bit register that holds other information as well. It's called the processor status register. I haven't mentioned it to you yet because I haven't needed to, and I tell you 10,000 things, and so I try to keep it simple and give you this info when you need it. So there's a register that saves the state of the processor, or the process that's currently running. So the first 3 bits in it are the condition codes. Bits 8 through 9 store the priority level of the process that's currently running. Remember, 0 is low priority, 7 is whiskey priority. And then 15 is 1 or 0, and that's the privilege of the thing that's running. And there's only 2 choices. You're either user privilege or supervisor privilege. Supervisor privilege gives you access to the operating system stuff. User privilege does not. So that gets checked. You'll see sometimes when you're doing something, if the privilege isn't right, you'll get an error. So that's what that is. So we need to save that whole register. We're going to save it somewhere, and we need to save the program counter somewhere. So one of the solutions we could do is that whenever we detect an interrupt, we could take those two registers and store them somewhere special. Either another set of registers or maybe somewhere in memory. And we can just take those and store them somewhere, like hard code, where they're gonna go to get saved. The problem with that is that an interrupt can be interrupted by another interrupt. The people at Diablo, there was an emergency, they're running around trying to fix the power plant, and then all of a sudden, we run out of whiskey. So that interrupt's gonna get interrupted and we're gonna go to the store. So we can't then just save the program counter from that first interrupt and processor from the first interrupt into that same hard-coded memory location, because we'd be overwriting what we needed for this program. So we have to be able to use a stack to go ahead and, when this guy gets interrupted, push on its program counter and PSR, the processor status register. And now, so this is the top of our stack. And then we're running the code that is servicing the power plant, and then that gets interrupted, so we push its PC and PSR onto the stack. And so then when we finish our run to get whiskey, we come back and we can pop these off and put them back for our power plant program. Now we're here, and when the power plant program finishes, we can pop those off and restore them for this program, and now they're back. And the register saving and restoring, that needs to be done by the interrupt service routine itself, which it can do, because it knows what it's gonna mess up and what it isn't. Questions on that? Let's go over, this whole slide, right here was based on the discussion we just already had about why we can't store it, why we can't store the PC when we get over here, because the PC's been messed up already. Why we can't just have a special hard-coded place to do it, because interrupts can interrupt other interrupts, so we need a stack. That's what this slide is. So we actually have, well, most machines are gonna have two different stacks, a user stack and a supervisor stack. And our supervisor stack is a special region for memory that we're going to use to store these things in when the interrupt happens. And like I said earlier, usually there's a special register that is the stack pointer for the supervisor stack. We don't have that here in the LC3, so we're just gonna use R6 to be our supervisor stack pointer. And nicely, what happens in the LC3 when an interrupt happens, wherever you have R6, it's just gonna know that that's your stack pointer. So when we go to play with this, we're gonna write a program that does this. We will, before our code starts, we will set R6 to where we want the top of our stack. It's safe to set it to 3000 because remember, it'll decrement when it does a push. So it'll decrement to 2FFF into operating system space and then push the data on. And it automatically uses R6. So when you turn on interrupts in the LC3, when a key gets pressed, you can see if you set R6 to that, and then you go look at memory location 2FFF and 2FFE, you'll see the program counter and the PSR for the process that was interrupted. It'll just put it there for you. The hardware does it. There's no software that needs to happen. It automatically happens. Where's our time? Anybody know what the actual time is? I can't see it on here.
It's like
57.
58 or 57? Okay. I will do, okay. I'm gonna do these next two slides and then we'll quit. So here's kind of a step-by-step what happens to when an interrupt occurs. So first thing that happens, right here we detect, oh, an interrupt has happened. So the PSR, that's the processor status register, and the program counter for this program get pushed onto the stack. Then we go ahead and we change the PSR. When an interrupt happens, we get into supervisor mode. So we set that bit 15 to 0. And then we set the PSR to the priority of the interrupt. So if this is the Diablo interrupt, we set the priority to 6. And then we set the condition code part of the PSR to 0, all of them, so they're all zeroed out at that point. step 5 is how we get to the service routine. So depending on the interrupt being serviced, just like the keyboard and, or like our trap, if we have a trap vector, like trap 20 is hex 20, trap 21 is hex 21. There's a table to say where to go if we want to do trap 20. It's super similar with interrupts. So every interrupt has an interrupt vector. So for the keyboard, the interrupt vector is 80. The problem is we're not going to go to memory location 80 to see what to do when the interrupt happens because that's in the trap vector table. There could be a trap 80. So our trap vector table is here through, that's the trap vector table. Right below that is our interrupt vector table. So what we do is whatever the interrupt is, we add 100 hex to that. And that's where we go in memory to look to see where that interrupt should be, where the interrupt service routine is. So in my example, so when the key is pressed, we should go there to service that interrupt. And it's just a lookup table, just like the trap vector table. So we load that into the program counter, this memory location right there. And then we put that in the program counter, and then we start fetching. And then when we want to go back, we have to be able to return from the interrupt, which I think our time is up, so I will do return from interrupt probably on Monday. And then we'll stop and we'll study for the midterm. Thank you, Joe, and hi people at Grace Halberd.